Today we're going to perform the lab as a group to try to find some relationships and some numbers involving a ball undergoing projectile motion. So here's what's going to happen. So we're going to take one ball as a group on the left side of the room. Somebody's going to throw that ball up at an angle. It doesn't matter exactly what that angle is. It's going to follow a path that looks something like this. You guys remember what that path is called? By now you should, right? Yes, it's called a parabola, right? Then we're going to take that data, import it into a software program that I have on my computer, analyze, it's called Tracker, by the way. We're going to analyze it together to measure the position and time of this ball at every frame along the way. So that's going to give us some nice data for time, for horizontal position, for vertical position, and for vertical velocity. You're going to end up with a table that looks like this. After we collect this data and I import it into my software program, then I will save that data and share it with you on Google Classroom. Right now the assignment's been posted. There's no data yet because we don't have data, but I'll add that to the assignment after we collect it. So you don't need to worry about writing down all those numbers or anything like that. All right, so your data table is going to look something like this. Time in the first column, horizontal position in the second column, vertical position in the third column, and vertical velocity in the fourth column. I'll caution you that the software program that I use doesn't label the columns well. So if you're just copying it directly from what I share with you, you're not going to get full marks because it's not going to list the columns the way that it should. So you're going to want to change that. You can easily change that, but that's your responsibility to change that into columns that are labeled like this, or at least more or less like this, all right? Once you have your data, you're going to plot 3 graphs. Now, one graph is going to be to find for us a horizontal relationship. To plot that graph, you're going to use horizontal position and time. So the first 2 columns. The first graphic plot is going to look like, well, I'm not going to tell you what it's going to look like, but your axes are going to look like this. Whatever the shape of that graph is, and don't forget to put the title in, don't forget you're labeling your axes properly, don't forget to put the units in, and so on and so on. Whatever that graph looks like, I want you to draw a trend line, and I want you to draw a best fit line. That's right, I want you to label the equation. And then I want you to answer these 2 questions. What does the shape of the horizontal position versus time graph represent? So if it's a straight line, what does it represent? If it's a curved line, what does it represent, right? Acceleration, constant velocity, not moving, whatever the case may be. And then the question number 2 says, what is the horizontal velocity of this particular projectile? So you're obviously going to get that from the graph. Determine the velocity of this projectile. Horizontal, not vertical, because we're only plotting horizontal position versus time here, right? So only the horizontal velocity of this particular projectile, and then you're just going to justify that. How do you know? That's effectively what a conclusion would be, right? If we were doing a full lab right now. What is the velocity? How do you know? The next thing you're going to do is go back to your first column and your third column. So now you're going to plot a graph of vertical position versus time. This is on the template for you, by the way. It tells you what to do. Vertical position versus time. You're going to plot a trend line for this. You do not need to display the equation for this one. Okay, that's a hint as to what it might look like. You do not need to display the equation for this one. It's just simply going to be the data. Make sure you put in the title, make sure you put in the units, all that stuff, the data, and then the trend line, the best trend line that you can find that fits this data. Then you're going to answer question number 3. What does the shape of the vertical position versus time graph represent? So if it's a straight line, what does it represent? If it's a curved line, what does it represent? If it's a flat line, what does it represent? Finally, you're going to plot the first column and the last column. And you remember what I said here on the last lab? When you're plotting two columns that aren't beside each other, what's the easiest way to plot those in a graph? Copy them over, right? Like make a new table of time and vertical velocity when you go to plot that graph. You can select these two columns from this table to plot the graph, but personally, I find it easier if you just create a new table. Time and vertical velocity. Now, that graph is going to be your third graph, vertical velocity versus time. Make sure you put in the title, make sure you label the axes and the units and so on. You also, of course, want a trend line. We always want a trend line. And in this case, you're also going to display the equation. Then you're going to answer the fourth question. What is the vertical acceleration of this particular projectile? Not the horizontal acceleration. We know there is no horizontal acceleration, right? It goes at a constant velocity. What is the vertical acceleration? Makes sense we're going to get the vertical acceleration from this graph because it's vertical velocity versus time. Now, I'm not going to tell you how to find the vertical acceleration from the graph, but once you see that graph in front of you with the trend line and with the equation displayed, I hope that it becomes relatively obvious to you how you're going to find that acceleration. I'll just remind you, by the way, for the two graphs that you're displaying the equation for, you can display that r squared value if you want, but that's not the one that I need to see. The one that I need to see is the one that says 0.724x plus 0.003, or whatever the case may be, right? It's something x plus something else. Got it? Something x plus something else. If you want to display the r squared value to see how good your data is, that's fine, but we're not using that number anywhere other than to tell you how good your data is. Now, how are we going to actually get the data for this? How are we going to fill in this table? We are, as a group, in a moment, going to set up a camera back here, my iPad back here. We're going to have somebody toss a ball lightly, this big yellow tennis ball, in a projectile path, a parabolic path. It might take a few tries because we want to get the entire path of the projectile in the frame of the camera. We don't want it to jump out of the screen anywhere, the frame anywhere. Now, there's a couple other things we need to do. Somebody's going to, I'll do the video, somebody's going to throw the ball, and somebody's going to throw it and practice it enough so that they get it all in the frame of it. Somebody else is going to stand right underneath the path of the ball, like directly underneath the path of the ball, with this meter stick in their hand. And what I'm going to ask you to do, whoever's the volunteer that does that, to put two fingers, one finger at each end of the meter stick. When we're going to analyze this in the tracker software that we're going to use, the tracker software needs to be able to define a meter. If it's going to measure the horizontal position and the vertical position in meters, it needs to know what a meter is. So we're going to tell it what a meter is by putting a meter stick in the frame. Got it? The time is easy because it knows the frame rate of my iPad. The frame rate of my iPad is 30 frames per second. And the computer knows the frame rate of that iPad, so we can, from that, easily calculate the time. But we need to tell it what a meter is. We could define a yard, we could define 5 meters, we could define whatever distance we wanted. It would work, but the easiest thing is just to hold that meter stick in there, because then we know exactly what 1 meter is. Again, whoever's doing this, I'll ask you to put your fingers at either end, because it makes it a little bit easier for us to see it in a camera frame, to select the ends of the meter stick when your fingers are at the end of it. All right? I'm going to pause the podcast here for a few moments until after we get our data collected, and then I'll unpause it when we start actually using the computer program to get the numbers to fill in this table. All right, now that we've collected our data, we want to import now that we've filmed the projectile, the tennis ball moving through the air, we want to actually bring that video into this software program we call Tracker. We're going to do that by opening it up. We're going to find it in my drive, here. And what was it called? What was it called? It was called 0763, so I'm going to open that. It's going to take just a few moments here to bring it in. And now you can see this video that's in the software program tracker. Now what I want to do is define a meter. I'm going to do that by clicking on this calibration stick. You can see right here that that's got that labeled as 100 centimeters. I'm going to actually move that down there to the meter stick, where the rose was, and then I'm going to stretch it to the other end of the meter stick. So what we've now done is told the software program that that distance is 1 meter. Now that works horizontally and vertically. I don't need to define it both ways. The computer knows whatever plane it's on, that is 1 meter. Now I'm going to just go a couple frames ahead to where the ball was released. Let's go back a couple frames. Okay, the ball has been released. I'm going to define that my XY axis now, that being my 0 point. So I'm going to move my XY coordinate system to start here at the very beginning of where the ball was released. So that's basically my 0, 0 point. Now I think I've got that XY coordinate system kind of rotated a little bit. I do. There. Angle from the horizontal, it says, is 0. Perfect. Okay, so the ball is released at that point. Now, if I keep going, if I advance it frame by frame by frame, you're going to see the ball going up, a parabolic path. We're going to measure all of those points, the position and the time of that ball until it gets to that point, until it gets to the 0 point. Okay. So let's go back to the start. Not when it was being released, but let's go back to the start of our coordinate system, which is right here. And now let's start marking some points. We're going to do that by creating a point mass. And then I'm going to, oops, pretty loud on me. There we are. Okay, so my point mass has been created. Now I'm actually going to make a mark on the screen wherever that ball is on each frame. So I'm going to do that by pressing Shift and click. This will be my 0, 0 point. And I'm going to Shift click here, and I'm going to Shift click here, and so on and so on. Wherever the ball is, I'm going to Shift click to mark where the ball is. Now remember, the computer already knows what a meter is, so it's measuring the distance right now, and it knows what a second is as well, based on the frame rate of my iPad, which was 30 frames per second. So basically, every 30 frames, it's saying, okay, or every frame, it's saying that's 1/30th of a second. Let's do one last one. There we go. So now we see a bunch of data over here. T, X, and Y. That's actually the time, which is what I want. It's actually the horizontal position, which is what I want. X is the horizontal position. Remember, you need to relabel that, because X is not a good enough column title for it. You also need the units for it. I don't want Y position. No, I did want Y position, but I also want Y velocity. So I'm going to go in there, and I'm going to check off VY for Y velocity. And now I see the 4 columns that I want. Time, X position, Y position, and Y velocity. Again, you need to label them better. You need to put the units in there for it. By the way, just a quick little thing. I just noticed this actually. When I was going over this yesterday, I did not notice this. Look at the meter stick that Bose was holding. Can you guys see the number that's above that? What does it say? No, it just says a number. It says 100.0. 100.0. What is that telling us? It's not measuring in meters, is it? It's measuring in centimeters, right? So everything is for you is going to be centimeters per second. centimeters per second squared. Got that? It's okay to stick with those units. Just know that, of course, you're not going to get 9.81 if it's centimeters per second squared, right? 981 maybe, right? It's okay to stick with centimeters. Just make sure you label those units properly. All right, there's my data. I'm going to copy over all that data. Now I'm going to go into my Google Drive. And I'm going to save that data, and then I'll take that data and add it to Google Classroom, and you guys will do your thing with that. So we're going to title this Projectile motion data, and they're all going to use the same data. Remember what you're going to do though, right? Make a copy. Actually, I'll tell you what, I'm going to make this view only. So in order to force you to make a copy, you're going to have to physically copy the data and create a new spreadsheet. Does that make sense? Paste that data in here. There we go. Now I'm going to go into my projectile motion lab. Just going to add this for you guys. Oops, I don't want to add a new sheet. That's not what I want to do. I want to add your projectile motion data. I'm going to make it students can view file. Again, that means that you're going to have to create, you're going to have to copy and paste that data into a new one. All right, it's up. You guys can grab the Chromebooks, start doing your thing.